Recording.
Okay, so we can start. So thank you everybody for coming. My apologies for the delay. That is entirely my fault. But now that we've sorted out the time zone changes and everything, it is my great pleasure to welcome Robin Snyder here, who is going to be talking to us about the role of luck in reproductive skew and individual success. So without further ado, please, Robin.
Thanks, Gary. Everybody, I can't see you. Can someone give me an indication that you can hear me?
Yes, we can hear you.
Great. So before I carry on, I want to point out that everything today comes from my collaboration with Steve Elmer, and I want to thank the National Science Foundation for their financial support. So this is the monthly income distribution in the United States from 2013. It is to no one's surprise that this is a highly skewed distribution. And this immediately brings up questions. The most obvious being, who are these people way out on the right-hand tail? And how did they get to be there? And are there things I could do to become one of them? There are lots of people on Amazon who are happy to sell you books to cater to this curiosity. As ecologists, however, we also encounter skewed distributions and have a similar curiosity. There are many species for which the distribution of lifetime reproductive output is highly skewed. Most individuals produce few or no offspring, while a few individuals produce very many. And we have similar questions. So in this seagull study, 22 pairs out of 110 produced 0 chicks over the course of their lives, but there were 11 pairs that hatched over 20 chicks over the course of a lifetime. And what is it about those 11 pairs? Gulls can eat fish, which is harder to find but more nutritious, or then it can eat refuse, which is easy to find but less nutritious. And these authors found that birds with long breeding lifespans and a high breeding success had a diet that was majority fish. And so that's, in either case, whether we're thinking about lifetime reproductive output distributions or financial distributions, we're curious to know what is special about these individuals way out on the tail. On the other hand, you have people like economist Robert Frank, who wrote a book saying that talent and perseverance are necessary but not sufficient for exceptional financial success. Turns out you also need to be lucky. Spoiler alert, this also turns out to be true for lifetime reproductive output. And so maybe a better question is not so much what's special about these individuals, but in what way did these individuals get lucky? More precisely, given that an individual has exceptional lifetime reproductive output, what can we infer about them, either about their traits or the forms of luck that were influential in their success? Or we could think about the shape of the distribution. We might ask, why is the distribution as broad as it is? Which we might want to measure with variance. Or we could ask why the distribution is as lopsided as it is. In economics, there are various measures of income inequality. In ecology, we tend to talk about reproductive skew, that is the skewness of that LRO distribution. And that immediately brings up other questions. So how much are reproductive skew or variance driven by individual quality? How much by external factors like the environment? How much by random chance? And at what time of life are each of these most important? And do the answers to these questions depend on life history? And finally, we might want to think about the implications of the distribution shape. So in the social sciences, people ask about the economic, social, political, and health consequences of income inequality. In ecology, we note that if reproductive skew comes from heritable differences between individuals, that's a huge opportunity for selection. On the other hand, if the skewness is coming from random chance or non-heritable differences between individuals, then skew changes the consequences of genetic drift. The probability of fixation and the mean time to fixation no longer depend just on the variance of lifetime reproductive output. And I'll have a little bit about that at the end. For the modeling framework, we used matrix population models and integral projection models. Many of us have seen the online databases, Compadre and Comadre, managed by Rob Salguero Gomez's group. We use those as well. Let's talk about what drives distribution shape first. So here's a tale of two lives. On the x-axis, we have size Z. This came from a model for tropical canopy trees. On the y-axis, we have 6 light levels. So here's an environment Q. And we can imagine a life as a random walk on this landscape, where the color of the landscape tells you your expected future lifetime reproductive output given where you are right now. And so we have one individual that wandered for a while. It was born in a lower light environment, a slightly larger size. And it died at some point. And then we have another life represented by this dashed line that lived for a longer period of time. That individual was born at a lower size, but in a better light environment, and kind of wanders around and eventually makes its way up into a high light environment, probably through growth, into the canopy. And then it gets into these areas of the graph that have high expected future lifetime reproductive output. And this is a random walk. We're moving around in size, we're moving randomly in Q, and that has consequences. More mathematically, we divide each time step into updating fecundity first, and then survival, and then growth, and then if there's a varying environment, the environment. And we ask how the conditional distribution of lifetime output, given, I've got echo. I think someone maybe has their mic on. If you could just check, everybody. Okay, so we ask, how does the conditional distribution of lifetime reproductive output, given all events up to the present, change when we learn the outcome of one more uncertain life event, like this survival at age A? And so removing survival luck at age A by learning the outcome of this transition in red will make the conditional variance go down because there's less uncertainty about what happened over the course of life. And that decrease in variance, we're going to call the contribution of survival trajectory luck at age A. And then, of course, we also have growth trajectory luck, environment trajectory luck, and fecundity luck corresponding to these other transitions. In the absence of trait variation, as we condition on more and more of an individual's life, their variance will get less and less until once we've conditioned on the entire life trajectory, we know everything that happened, and so the variance is 0. Now, I mentioned traits. We're defining traits as fixed differences between individuals. That could be a genotype, it could be a birth date, your mother's weight. I do not want to upgrade my operating system, but thank you for asking. The location of a sessile individual or a fixed behavioral syndrome. And the contribution of trait variation is the total variance minus the sum of all the luck contributions. We can partition skewness in exactly the same way. Note that knowing one more thing that happened could make the future lifetime reproductive distribution more lopsided or less lopsided. And so contributions to skewness can be positive or negative. A bit more mathematically, we're going to take our original state space and we're going to bump it up to a size 4 times the original dimension for the 4 phases of the time step. So maybe our state space is characterized by size Z and environment Q, and for some applications, total number of kids so far, K. Now in our extended state, this first block represents the state just after the environmental update in the previous time step. And then we're going to move to the next block. This is the state just after the fecundity update, Just after the survival update is the third block, and then finally this fourth block is just after the growth update. So for example, just after the growth update, the state is a bunch of zeros. All of our non-zero numbers are in that fourth block, and we've got the updated number of kids, k at a+1, updated size, z at a+1, now that survival and growth have happened, but we have not yet updated the environment q. And our transition matrix looks like this. So F bullet here updates only the number of kids, and it moves us to the next block. S bullet updates only survival, and it moves us from the second block of states to the third block of states, and so forth. So if we apply this giant matrix at the beginning of the time step, we move from the first block to the second block, and now we've updated the number of kids, but not yet size or environment. We calculate moments of the distribution using Markov chains with rewards. Each transition between stages is associated with a reward, representing, for example, the mean reproduction for that transition or the second non-central moment, etc. And you can find out more about that by reading Van Dalen and Caswell 2017. And we do this in the extended state space so that we can update. Hey, Bob.
You know, I have a suggestion.
Yes.
Yeah, that's my suggestion. You got it. Just leave it here.
Bob, if you could turn off your mic. Thanks so much. We're going to do this in the extended state space so that we can update that distribution at the end of each subdivision of the time step. Some common confusions that have come up when I've given this talk in the past. Isn't it lucky to be born with good traits? Yes, but that's not what we mean by luck here. What if some of the luck in survival, growth, and reproduction is coming from trait differences that we simply haven't measured? Absolutely, that could be happening. What we're doing here is we're drawing out the implications of a given model, and if it's not in the model, then we can't talk about it. Note that we are not studying reproductive skew due to social dominance or differential skew between the sexes due to a mating system. These are cool questions. They're just not our questions for right now. So here's the first result. Reproductive variance is mostly luck. And this is not just what our team found, but other groups like Caswell's group and Tolj-Porkar's group. Here's a model of kittiwakes. It has a normally distributed quality variable such that high quality individuals have higher survival and higher breeding probability. Reproductive variance is 61% luck. Three-tip sagebrush we chose as our trait the competitive environment at birth, knowing that that had a big impact on survival of small plants. Variance was 99.7% luck. There may be some other trait that matters more, but it wasn't competitive environment at birth. Roe deer. People have talked about an important trait there being how early or late in the season you were born. Since if you were born early in the season, you will be bigger by the time winter comes around, and that's going to affect your early survival plus your body mass as an adult. 99.4% luck. And then we looked at fulmars as well. These are long-lived seabirds with 3 fixed behavioral syndromes governing a fecundity survival trade-off that affects breeding probability and juvenile and adult survival. Reproductive variance was 80% luck. Reproductive skew is also mostly luck. The red bar represents the contribution of traits, and while that is certainly not negligible, it is far from dominant. I was really concerned when I first saw these results. I thought, oh my gosh, if success is largely determined by luck, does that mean I broke evolution? No. Remember that evolution happens at the population level, where luck tends to average out. And so those phenotypes with higher average lifetime reproductive output will tend to increase in frequency. If you want to think about it a different way, in this picture, Steve has more lottery tickets than I do, and that does give him a competitive advantage. But if he wins, it will still be mostly a matter of luck. So why does variation matter more? Selection is maybe one answer to that. If individuals with the right traits are far more successful, then selection will weed out the less fit individuals. Now that assumes that whatever we're calling success is related to fitness. In this talk, it is fitness, so that's fine. And that traits are heritable. Okay, so far we found that the shape of the lifetime reproductive output distribution, or at least its first 2 moments, is driven mostly by luck, not by traits. And so now we want to ask what kinds of luck are most important, and at what points in life, and does it depend on life history? So I've got a bunch of plots that follow that look like this. I've got age on the x-axis, and on the y-axis, I have contributions to reproductive variance, and I've got colored lines for each of the type of luck. And where you see peaks, these are times of life where that form of luck is particularly important. And we might think about that as some sort of critical window in an individual's life. The peak timing comes from a balance between being in a stage where what happens next matters a lot and being relatively likely to still be alive by that point. It may be that what happens to 500-year-old oaks in the next time step matters a lot because they produce many, many offspring. On the other hand, it's very unlikely that any one individual is going to live to be 500, and so you're not going to see a peak way out at age 500. Let's look at variance first. Snow geese have slow, largely deterministic growth. Their fecundity doesn't vary a whole lot with the environment. They're putting out, 0 to 2 chicks per year, relatively long-lived with an average lifespan of 4.6 years. The way to have lots of offspring is to live a long time and reproduce many times. Okay, so as you might expect, reproductive variance is driven by survival trajectory luck. That's this black line. On the other hand, we have woolly sculpins. Their average clutch size varies tremendously with environment, between reproductive failure and 21.5 offspring on average in the best years. They don't live long at all. Most individuals live long enough only to reproduce once at most. And so you kind of just have to get a really good year when you're up for reproduction. Unsurprisingly, reproductive variance is driven by environment trajectory luck. Although we also see that survival trajectory luck is not insubstantial. You do need to at least live to become reproductively active. And its survival trajectory luck is especially important when you're really young, because if you die young, then what might have happened later doesn't matter. Artemisia ordosica is a desert shrub. It has highly labile growth. It grows and shrinks. We don't have reproductive data for this species, so as a proxy for reproduction, we use number of years spent at least 40 centimeters, because that's the size range that produces most of the offspring. Because it has such labile growth, for most of its lifespan, reproductive variance is driven by growth trajectory luck, this orange line, and it peaks right before most individuals are hitting that size transition where they start to produce a bunch of offspring. On the other hand, survival trajectory luck, the black line, is of course really important when you're young because you don't want to die young. And finally, here's a tropical canopy tree. Again, slow, largely deterministic growth with a long time before reproduction. Our proxy for reproduction is number of years in the canopy. We have a peak in survival trajectory at the very beginning of life, don't die young. We have a peak in growth trajectory luck at the beginning of life, which again is because of survival. You want to grow quickly out of those very small size classes where mortality is high. But then we also see this second peak in environment trajectory luck just before individuals typically hit the canopy. That's that purple line, because being in a good light environment can then give you a surge of growth, which pushes you into the canopy. And then once you're there, you need to survive long enough to take advantage of that fact. So now we've got a peak in survival trajectory luck just after the purple line. So we found that what kind of luck drives reproductive variance depends on life history. And luck matters a lot when you're very young, because if you die young, then nothing else matters. Luck sometimes peaks again around the time of initial reproductive success, if that's substantially later in life. So we saw that tree example. So for example, environment luck can put you over the threshold, and then you need to survive long enough to take advantage of it. For skewness, on the other hand, the dominant contribution is always luck and survival. So here's the snow goose, which had that slow plodding life history. Skewness is dominated by the black line, survival trajectory luck. But here's the sculpin with wildly varying fecundity, short-lived sort of boom-bust cycle. Its skewness is still dominated by survival trajectory luck. And that's true for all the other case studies we looked at as well. What about trait variation? That can increase or decrease skew. We only had 2 case studies where we had trait variation, Fulmars and kittiwakes. Our speculation is that quality variation, such as in the kittiwakes, will increase skewness because high quality individuals are better at everything, while variation along some life history trade-off, like with the Fulmars, is decreasing skewness. But it would be great to get some more case studies. Okay, so unlike reproductive variance, reproductive skew is so far always driven by random variation in lifespan, survival trajectory luck. And trait variation can increase or decrease reproductive skew. We are speculating that variation in quality increases it, while variation along a life history trade-off decreases it. Enough on distributions. What about those individuals way out in the tail? What can we infer about exceptionally successful individuals? Are they particularly high quality individuals? What we can do is calculate the probability of having a particular trait value on lifetime reproductive success, R. We do that by calculating the distribution of state at death and adding the number of kids to the state variable. That gets us the distribution of kids at the time of death, and then we can condition on trait and use Bayes' theorem to reverse things. Here are the results for the kittiwake. On the x-axis, I've got lifetime reproductive output, and here's the marginal distribution. It's crazy skewed. On the y-axis, I've got quality with the population mean represented here in the middle with this dashed line. Every vertical slice through this heat map gives you a distribution quality for a particular lifetime reproductive output. So we see that if you're out here in the upper 10th percentile, we are really quite confident that you are of above average quality. Almost all of this distribution is above the dotted line. Whereas you're down here in the bottom 50%, really can't say. And even if you're at the 75th percentile, you could be high quality, you could be low quality. So what we're finding is that high quality is necessary, but not sufficient to be way out in the tail. And here, to look at it another way, here's the distribution of quality in black for those at the 50th percentile of LRO. Here's what it is for the 90th percentile of LRO. Clearly distinguishable means, but there's a lot of overlap. So exceptionally successful individuals tend to have above average traits, but you can still be above average and still have modest LRO, which is exactly what Robert Frank was writing about in his book, Meritocracy, with financial success. We saw that survival trajectory luck tends to drive reproductive skew. That leads us to ask, are exceptionally successful individuals particularly long-lived? So we're going to calculate the probability of lifespan conditional on R. Here's a similar plot for a snow goose. Again, every vertical slice through this image gives us the distribution of lifespan conditional on lifetime reproductive output. And there's a pretty tight correspondence between the two. As you move further out into the reproductive output tail, you're moving further out into the lifespan distribution tail. So exceptionally successful individuals are almost always exceptionally long-lived individuals. There are some modifications to that story we need to make. So here are some more case studies. We've got snow goose on the left. It has low environmental variability and fecundity. Ambonium is a marine snail. Ambonium castatum has medium levels of environmental variability and fecundity, and now we're seeing a weaker correspondence between lifespan and lifetime reproductive output. And here's that little woolly sculpin, which had extreme levels of environmental variability, and now there's a very weak correlation between lifespan and lifetime reproductive output. So as environmental variability and fecundity increases, as we go from left to right, that central probability interval gets wider. And we notice too, these two red spots here for the sculpins. The most probable lifespan is 2 for two very different values of LRO. We're going to talk about both of these issues. Let's talk about the first one first. Perhaps the distribution of lifespan conditional on LRO is wider if fecundity varies a lot with the environment, because a really good year can substitute for a somewhat shorter life. So as a test, we set all mean clutch sizes to the environmental average and asked if that central 90% probability interval gets narrower if we remove that environmental variability. And the answer is yes. Here's what that looks like for Ambonium. With environmental variability, we have the yellow region that represents the 90% central interval in percentile of lifespan. If we take away environmental variability, we collapse down to this orange central interval. And we see in particular at high lifetime reproductive output, removing environmental variability really tightens up that central interval. So depending on life history, getting an exceptionally good year can partially compensate for living less long. And then we want to think about those two big monster eyes there. There's a second route to exceptional success, at least with some species, and that is to get a super good year when you first become reproductive. So for sculpins, they can first become reproductive at age 2, where their average clutch size in that really good year was 15 offspring. And so here's that blotch representing that other path to success. Maybe you only reproduce once, but you got a really good year, and now you're already way out on the tail, even with only one reproductive bout. If we remove environmental variation in fecundity, this plot starts to look a whole lot more like the plot for the snow geese. Much tighter correspondence between lifespan and reproductive output. So if the best years have very high fecundity, getting a rare, exceptionally good year at the right time is an alternative route to success. And then I'm briefly going to talk about the implications of reproductive skew. Neither Steve nor I is a population geneticist, so this is going to be brief. There is some suggestion that reproductive skew causes slightly beneficial mutations to have a lower probability of fixating, but to fixate faster if they do. And one nice paper about that is Alvin and Stefan 2023. Our intuition about this is that if the mutation is found in one of the few exceptionally successful individuals, it fixates quickly. And if not, it doesn't fixate at all. Nonetheless, no one has actually varied skewness as they have held mean and variance constant. This is beyond our skill set, frankly, and we're hoping that someone will take this up. So, summarizing, both reproductive variance and reproductive skew are driven mostly by luck, not by inherent differences between individuals. Again, in the absence of social dominance. Reproductive variance can be driven by luck in survival, growth, or getting a good environment, depending on life history. Reproductive skew, on the other hand, is driven by random differences in lifespan, luck and survival, independent of life history. Trait variation can increase or decrease reproductive skew. Variation in quality, we think, might increase it, while variation along a life history trade-off decreases it, but that is based on exactly 2 case studies, so take that with a grain of salt. If expected fecundity doesn't vary much with the environment, those with exceptional LRO lived exceptionally long lives. If expected fecundity does vary a lot with the environment, then those with exceptional lifetime reproductive output had some combination of long life and particularly good years. And with that, I will say thank you and take questions.
Thanks so much, Robin. I don't know if I should take this, but I will anyway. So if you have any questions, then you can raise your hand in the participant list, and I will call on you. Okay, while people are pondering, maybe I will ask. Oh, but Chris, go ahead.
Sorry, my camera didn't make the transition. The I don't. That's why I was late. I don't know what went wrong. Thank you so much for the talk. Do you get the feeling that some species lean into being lucky, in the sense that they try and evolve to take advantage of luck in a particular way? And what would that look like if it was happening?
Yeah,
or do
so
species do the opposite and try and minimize the effect of luck to like?
I certainly think that's true for environmental luck. You know, you've got sort of generalists and specialists, and okay, maybe you can't control your sensitivity to environmental conditions, and snow geese have this very mild sensitivity to the environment just because that's what they are, that's who they are. But maybe that is evolved, and that's some sort of buffered response to the environment. Whereas the sculpins are really specializing in particular years, and maybe that's adaptive as opposed to just what happens. If we think back to modern coexistence theory and all the stuff that Chesson talked about, we know certainly that environmental variability can promote species coexistence if it allows species to time partition their environment. And so maybe being really focused on those good years and being able to store the benefit from those years, that could be a successful strategy in an environment where you otherwise would be outcompeted. So I would think about that as maybe a, you know, focusing your strategy on taking advantage of rare good times, as opposed to sort of just trying to be a jack of all trades.
Yeah, it's just does it need the multi-species element? It's kind of interesting, like whether do you think this can extend into that, or is it just too far beyond?
Yeah, I mean, I think certainly once you get into multi-species, then we start seeing these different, am I going to be a generalist? Am I going to be a specialist? But of course, sometimes you don't have a choice, right?
Yeah.
Environments just suck. So I don't want to say that everything is adaptive, certainly.
Yeah. Yeah, thanks.
John, you got your hand up.
Yeah, thanks. Great talk, Robin. I love thinking about all this luck stuff. And I was wondering if you had thought about the role of luck in heritability itself, right? So if heritability is, well, narrow sense, it's the part of typic variation associated with variation in genes, and then we ascribe, some of the remainder to other stuff like the environment. Is luck in the environment there already in all these measures of heritability?
Oh man, my background in evolution is weak, and so I'm reluctant to comment on a definition. It kind of sounds like you're asking, how do we want to define this? Certainly when we're talking about luck, we're talking about realized fitness, not expected fitness.
Mhm, mhm. And I suppose maybe it's a bit more of an emergent thing than a trait per se.
Yeah, I mean, certainly at the population level, once you get a decent sized population, the fact that some individuals were lucky and some of them were unlucky just kind of washes out.
Mhm.
And we can imagine that we could sort of just attribute average level fecundity, success to everybody. It's only when you start getting into smaller populations that you start to think like, actually, it's just a few of them that were really successful and a bunch that weren't.
Mhm.
I'm starting to think about effective population sizes and drift and all of that.
Right, right. Okay. I mean, I don't really know where I'm going with that. I just feel like somehow it's wrapped up in
Can
there.
I mention something that may or may not be relevant at all? So if the heritability is the additive genetic variance divided by the total phenotypic variance, then the total phenotypic variance will be influenced by the fact that it's the variance of a skewed distribution, and that could play tricks. And most of this, I mean, I'm also not a geneticist, so correct me if I'm wrong, but most of these things are derived assuming normal distributions.
Mhm.
And if it's not, then that will distort things, I would imagine. So reducing a distribution to its variance is throwing away information.
Mhm.
But I'm wondering if the general effect could be that if these distributions are a bit more skewed, then the variance that one measures is larger than one would with a normal assumption. Is that the case? What that would mean, if that's true, I don't know if that's true, but if that is true, then measured heritabilities are actually underestimating true heritability, whatever that might mean.
Yeah, although again, I worry about fixing some definition of heritability, but then people then going and using that definition, direct definition of heritability, where under the hood we've all assumed normal distributions. Same thing for effective population size. It's like you can define it if you want, but you can't use it in the same way that you did before if things aren't normal. So I skitter away from using those words.
That's a very good point. No, I mean, all of these classic quantitative genetic things, at least that I'm aware of, work on traits that are normally distributed, right? So the phenotypic variance is manifestly normal or close enough, and then people use it. And it's a good question, yeah, how that translates to these non-normal ones. Anyway, are there any other questions? I was wondering about maybe asking something which is reflecting on those cases that you were showing, Robin, about not just luck being important, but all important, like 99.4% of everything is luck. Or in the case of the deer population, it was 90 point something. So so of course it's a bit philosophical, what is luck? And if we really knew everything that's going on, then nothing is luck, presumably from that point on, then we can partition all the variation. But in this case, the variance unexplained is so big that one wonders if maybe something big was missed, like, I don't know, maternal effects.
Oh, I suspect that's so. I mean, in that study, you know, I was using a paper that said, oh, birth timing is really important. It's a great, let's choose that as our trait and see how that particular trait affects reproductive variance. But there are probably other forms of heterogeneity that we could have chosen as our trait, and maybe those were more influential. Chrissy, did you want to comment on that, or do you have something else? Yeah.
I just wanted to add that there are a bunch of case studies where we've looked at traits as a community. We've as a community of scientists, we've looked at traits that appear to have very big effects, and still luck dominates the variance in lifetime reproductive output. So I was involved in some work looking at rotifers that have maternal effects, and in that case, it is still like 70% luck or something. Within group variance is still super dominant, even when we have a really strong effect between groups. So I think we haven't cracked it yet. We're either measuring the wrong traits, or we need lots of traits or something, but even in cases where we have a trait that we think makes a really big difference, our models return that luck is more important.
Thanks. Yeah, are there any other questions or comments?
Yes, lots, but I can't formulate them.
Yeah.
Just email me.
Well, you can think about formulating them while Chris is asking something.
Yeah, Chris has got a question.
I guess I just had one more thing about kind of how much this luck is. I mean, that's all the luck at the individual level. Do you have a sense of which parts of luck kind of scale? Well, lots of them will scale down as you have more individuals because they're just even out. So which parts of luck do you think are most likely to kind of transfer through to the population level, if that makes sense, or is it not?
Oh, so instead of looking
out.
at lifetime reproductive output of an individual, you want to look at lifetime reproductive output of a population?
A little bit. So to some extent, the environment's going to be correlated across the individuals in a population lots of the time.
Yes. Yes.
And so the question then becomes,
yeah,
I guess, how can you trace that signal through and up in cases, I guess? That's an incredibly broad question, but how do we go through the next stage?
You've hit the nail on the head. I should say, we've been thinking entirely about individuals. All of this could scale up to being about a distribution for a cohort of individuals, except then you have to assume that they're all experiencing independent sequences of environments. We don't know how to make them experience all correlated environments mathematically. And so, yeah, I think environment starts to become more important if everybody's experiencing a good year or everybody's experiencing a bad year. I mean, this gets us back to models looking at the importance of demographic stochasticity versus environmental stochasticity. You know, thinking about extinction probabilities. Sure, if the populations are really small, demographic stochasticity is a big deal. But that quickly becomes negligible as population size goes up, but environmental variance is still going to drive extinction probability independent of population size. So yeah. Hey, Steve.
So I've another part to answering Chris's question, if that's okay. Sort of at the population genetic evolutionary level, the higher variance means that the standard models underestimate drift, but that just says that their parameters are wrong and the qualitative behavior stays the same. But high skew actually changes the evolutionary dynamics. So it gives you a different kind of coalescent, for example, in which you can have multiple mergers in one generation, looking backwards in time. So in terms of what scales up, I think it's really the high skewness, at least at the evolutionary level, that's more likely than the high variance to have qualitative implications. But in scouring the literature for papers on this, I think Robin and I found 4 population geneticists that are working on these questions.
Working in 2 teams. They're not
In
even.
2 teams, the 2 groups of 2 that are working on this. And so we sort of, ended our papers with pleas for more population geneticists to start thinking about the fact that realized fitness distributions are highly skewed.
No, thanks a lot.
And I'm hoping people out in the YouTube world are going to see this and think, yes, I want to do that.
Exactly. I don't know how many PopGen people watch the channel. We'll have to
maybe
invite
not.
them. Speaking of, we should probably, that's a discussion, I guess, for a different crowd, but we should think about inviting a population geneticist. Why not? Giza, if you have good ideas, let us know. Otherwise, sorry, any other comments or questions? If not, then thank you again, Robin, and my apologies for the rocky start to this. That was entirely my fault. But thank you for the great talk and the great discussion. And we will see you
next week.
Next week already, right? Yes.
It is already summertime in Europe, and we will not have any
issues, thankfully.